Hello, my name is James Walls, and in this tutorial I will be discussing the Anti-Markovnikov addition of hydrogen bromide to alkenes. Let's look at the general reaction. In the presence of peroxides, an alkene will react with hydrogen bromide to form an alkyl bromide product, where the bromine becomes attached to the carbon with less substituents, for reasons which we'll discuss later. The addition of hydrogen bromide to alkenes may display regioselectivity. Because hydrogen bromide is asymmetric, and in cases such as this where the alkene is also asymmetric, the addition of hydrogen bromide across a double bond may occur in one of two ways. In the presence of peroxides, a relatively fast reaction occurs where bromine becomes attached to the carbon with less substituents. This mode of addition is referred to as anti-Markovnikov addition. Alternatively, in the absence of peroxides, a relatively slow reaction occurs where bromine becomes attached to the carbon with more substituents. This mode of addition is referred to as Markovnikov addition. Let's look at the mechanism for the anti-Markovnikov addition of hydrogen bromide to alkenes. This transformation occurs by a radical chain reaction. As such, the mechanism consists of three main parts: initiation, propagation, and termination. Let's begin by looking at the initiation part of the mechanism. In the first step of initiation, a weak oxygen-oxygen bond of peroxide may homolytically cleave in the presence of heat or light to form two transient alkoxy radical species. In the second step of initiation, a newly formed alkoxy radical may abstract a hydrogen atom from hydrogen bromide to yield a molecule of alcohol and a bromine radical. Now let's look at the propagation part of the mechanism. In the first step of propagation, a bromine radical attacks a pi bond of an alkene such that bromine adds to the carbon that is less substituted, while the radical resides on the carbon that is more substituted. The result of this reaction is the formation of a tertiary radical intermediate, which is more stable and formed faster. Alternatively, if the bromine radical attacks a pi bond of an alkene such that bromine adds to the carbon that is more substituted, while the radical resides on the carbon that is less substituted, then a primary alkyl radical intermediate is formed. This intermediate is less stable and forms slower. Therefore, this alternative reaction is not favorable. Thus, as we have seen, formation of the more substituted radical is favored. In the second step of propagation, this faster formed radical intermediate abstracts a hydrogen atom from hydrogen bromide to form the addition product and a bromine radical. This bromine radical replaces the bromine radical consumed during the first step of propagation. This sets the stage for a radical chain reaction, and these propagation steps cycle many times over, and with each cycle, more product is formed. Aside from participating in chain propagation, these radicals may also participate in chain termination. When two radicals couple, chain termination occurs. This results in a decrease in the rate at which the addition product forms. Let's look at a few examples of how chain termination may occur. In the first case, two bromine radicals are shown to couple to form this sigma bond in this bromine molecule. In the second case, two alkyl radicals are shown to couple to form this sigma bond in this alkyl radical dimer byproduct. In the third case, an alkyl radical is shown to couple with a bromine radical to form this sigma bond in this dibromoalkane byproduct. Note, because of these chain terminating events, the rate of formation of the addition product dwindles. To compensate for these terminated chains, chain initiation, as previously discussed, must continuously occur to replenish consumed radical. To reiterate, the addition of hydrogen bromide to unsymmetrical alkenes may occur in two ways: via the anti-Markovnikov mode or the Markovnikov mode. In the anti-Markovnikov mode, a faster reaction proceeds in the presence of peroxides via a more stable radical intermediate, for reasons described in this tutorial, or via the Markovnikov mode, in which a slower reaction proceeds in the absence of peroxides via a more stable ionic intermediate for reasons beyond the scope of this tutorial. Lastly, it is important to note that the anti-Markovnikov addition of hydrogen halides is unique to hydrogen bromide. In other words, only hydrogen bromide may add to unsymmetrical alkenes in an anti-Markovnikov fashion. To understand this tendency, let's look at the energetics of the propagation steps for these shown radical chain reactions. For the addition of hydrogen bromide, both propagation steps are exothermic and favorable. For the addition of hydrogen chloride, the first step is exothermic, while the second step is endothermic and unfavorable. For the addition of hydrogen iodide, the first step is endothermic and unfavorable, while the second step is exothermic. Because both propagation steps for the addition of hydrogen bromide are exothermic, only the radical addition of hydrogen bromide is favorable. To summarize, in the presence of peroxides, hydrogen bromide will add to an unsymmetrical alkene to provide an anti-Markovnikov addition product. This reaction proceeds via a radical chain mechanism, and the anti-Markovnikov addition of hydrogen halides to unsymmetrical alkenes is only energetically favorable for hydrogen bromide.